Good morning everyone. I am Garima from BSc Chemistry Honors first year. Today we are going to start our chapter from Organic Chemistry BSc first year part 1 semester 1, that is Mechanism of Organic Reactions. Introduction. During the study of organic chemistry, we come across numerical reaction with the organic compounds undergoes. As we study these reactions, we not only want to know which reactants are give rise to which product, but we are also interested in knowing how it happens. Do the reactants change directly into product in a single step, or does the reaction takes place by several steps through the formation of reaction intermediate? The complete description of how a particular reaction takes place is called mechanism of the reaction. It tells us what bonds are broken and in what order, and which bonds are formed and in what order. It also tells us what kind of intermediates are involved and what are the reactive rates of different steps. We shall now consider some important notation and basic concepts involved in the study of organic reactions and their intermediates. Important notation. Reaction of organic compounds involve the breaking and making of covalent bonds and the movement of electrons from one side of to another. To indicate these changes, certain notation involve the use of different kinds of arrow have been adopted as discussed below. Curved arrow notation. It is very important notation in which a curved arrow indicate the movement of electrons as bonds in reactants are broken and new bonds are formed. It means that an electron pair move from atom to at the tail of the arrow to the atom at the head of the arrow. It is illustrated below with the help of reaction between water and hydrogen chloride. The electron pair move from O of H2O to H of HCl. The bond between H and Cl breaks and the electron pair move to Cl. The electron pair that moved from O form a new bond with H to give H3O positive ion. The electron pair of HCl give bond goes to Cl to form Cl negative ion. Similarly, reaction between acetylene and amide ion to form acetylene ion and ammonia may be as shown in this reaction. Half-headed arrow. As we will discuss in session 2.3, sometimes a bond between two atoms breaks in such a manner that each atom get one electron to the shared pair. To represent this type of symmetrical bond breaking and bond making, half-headed arrow are used as shown below. A, B, the two electrons are in between them. One will move on A and the other will move on B, give rise to A and B free radicals. Similarly, in the case of Cl2, one will move on one Cl, other will move on other Cl, will give rise to two Cl, each having 7 electrons. Next is CH4 plus Cl. The bond between CH will break and one electron will move on C, other will move on H, other will move from this in between the reaction, and one electron from Cl will move in between, which will give rise to HCl bond, and the bond will break from CH, which will give rise to CH3 free radical. It may be noted that half-headed arrow is used by showing the movement of a single electron, while a full-headed arrow is shown for a pair of electrons. Double-headed arrow. These types of arrow are placed in between the various conical structures of a substance which exhibit resonance. It is to indicate that the actual structure is a hybrid of these structures, which are hypothetical and not real. For example, double-headed arrow are placed between the two major conical structures of benzene to indicate the actual structure of benzene lying in between these two structures, which does not have any real existence. Types of bond cleavage. Reaction of organic compounds almost invariably takes place through the breaking and formation of covalent bond depending upon the nature of given organic compound, the attack of attacking reagent and reaction condition, a bond between two atoms of a molecule may be cleaved or broken in different ways, producing different type of reaction intermediate. The different possibilities are illustrated below by considering a covalent bond between two atoms A and B, homolytic cleavage or heterolytic fission or homolysis. This indicates the breaking of a covalent bond in such a way that each atom separates with one electron of the shared pair. A, B, one electron will move on A, other will move on B, give rise to AB free radical. This leads to the formation of highly reactive neutral particles containing odd or unpaired electrons and are known as free radical. It may be seen that the homolytic cleavage of bond is shown by using half-headed arrow in the pairs. Heterolytic cleavage or heterolytic fission or heterolysis. This involves the breaking of a bond in such a way that both the electrons of the shared pair are carried away by one of the atoms. One electron in between A and B will move on A, both the electrons will move, which will give rise to A negative plus B positive and vice versa. Heterolytic fission leads to the formation of charged or ionic species, one having the positive charge and the other having the negative charge. If both the shared electrons are taken away by the A, it would be converted into an anion and B into a cation. On the other hand, if both the shared electrons are rating by B, it would change into an anion while A would form a cation as shown above. Quite often, the ionic species formed by heterolytic fission bear the positive or negative charge on carbon. Such ionic species are known as carbocation, earlier called carbonium ion or carbon ion, accordingly as carbon carries positive or negative charge. It may be mentioned that if a particular covalent bond can undergo either homolytic cleavage or heterolytic cleavage under different conditions, the bond dissociation energy for homolytic cleavage is considerably different from that of heterolytic cleavage. In general, the values for homolysis are low while they are quite high for heterolysis. For example, the bond dissociation energy for CCl bond in CH3Cl for homolysis and heterolysis cleavage are 351 and 949 kilojoule per mole respectively. Homolysis cleavage CH3Cl will give rise to electron will move on C and other will move on Cl, which will give rise to CH3 free radical plus Cl free radical. Heterolytic cleavage CH3Cl, both the electrons will move on Cl, give rise to CH3 positive plus Cl negative. Reaction intermediate. The student is already familiar with the fact that in organic reaction the stating substance seldom changes into the product directly in one step. On the other hand, reaction first changes into intermediate substances called reaction intermediates, which ultimately yield the product. The reaction intermediate are generally very unstable and reactive substances which cannot be even isolated. We will now briefly deal with the main reaction intermediate which we often come across in organic chemistry. Carbocation, earlier known as carbonium ion. What are carbocation? A carbocation is a cation in which the positive charge is carried by a carbon which has only 6 electrons in its valence shell. For example, CH3 positive and CH3CH2 positive are simple carbocations known as methyl cation and ethyl cation respectively. A carbocation may be assumed to be a fragment of a molecule from which an atom or a group of atoms similarly bonded to a carbon get removed along with the pair of bonding electron. For example, if a bromine ion is removed from a molecule of tertiary butyl bromide, tertiary butyl cation would be formed as shown below. Tertiary butyl bromide will give tertiary butyl carbocation plus Br negative when both the electrons are moved on Br. Carbocation are very short-lived or highly reactive species. The reactivity of carbocation is due to their tendency to complete the octet of electron-deficient carbon. As a result, carbocation undergoes a variety of reaction. Formation of carbocation. Carbocations can be generated in many different ways. Some of the reactions in which they are formed are given below. First, direct ionization. The carbon hydrogen bond in many organic halides generate carbocations in the presence of a highly polar medium. Tertiary butyl chloride, when both the electron are moved on Cl, will give CH3 thrice C positive plus Cl negative. Alkyl chloride, when both the electron are moved on Cl, will give rise to allyl cation plus Cl negative. This method is of particular importance in the formation of relatively more stable carbocation. By the protonation of unsaturated compounds, unsaturated compounds such as alkenes, carbolic compounds and nitrile furnishes carbocation on treatment with proton donating solvent. For example, RCH double bond CH2 plus H positive will give rise to RCH positive CH3. C double bond O plus H positive will give rise to C positive OH. C triple bond H plus H positive will give rise to C positive double bond NH. From compounds containing an atom with a lone pair of electrons. When an organic compound having lone pair of electrons on an atom is treated with the acid, protonation of this atom takes place. This is followed by the elimination of a simple molecule containing this atom to furnish a carbocation. For example, alcohol plus H positive will give protonated alcohol, further gives carbocation. Ether plus H positive will give protonated ether, which will further give carbocation plus ROH by the decomposition of diazonium salt. For example, primary amine on treatment with HNO3 will give diazonium cation, which will further give carbocation plus N2 by the action of superacids on alkyl fluoride. For example, RF plus SbF5 on reaction with FSO3H will give R positive plus SbF6 negative. The term superacid is used for some exceptionally strong acidic solution such as SbF3 plus HF or SbF5 plus FSO3H dissolved in SO2 or SO2ClF. Structure of carbocation. The positively charged carbon of the carbocation is in sp2 state of hybridization. The three sp2 hybridized orbitals, which further lies in the same plane, are indicated in the formation of these bonds with other atom. The unhybridized p orbital remain vacant, thus the carbocation has a flat structure as represented on the right hand side. The bond angle across the positively charged carbon is nearly 120 degree each. Classification of carbocation and their order of stability. Carbocation are classified as primary, secondary, or tertiary according to the carbon bearing the positive charge, the primary, secondary, or tertiary in nature. In addition, the methyl ion having only one carbon is regarded as a special case. These figure shows methyl cation, ethyl cation primary, isopropyl cation secondary, tertiary butyl cation tertiary. It has been established that the order of stability of carbocation is tertiary, secondary, primary, then methyl. Explanation of relative stability of alkyl carbocation. A basic principle involved in discussing the relative stability of carbocation is that how does a given factor involve the magnitude of positive charge carried by the electron deficient carbon of the carbocation. It is apparent that any factor which leads to the disperse the positive charge by distributing it over the rest of the molecule stabilizes the carbocation. In contrast, any factor which leads to intensify the positive charge destabilize the carbocation. This relative stability of alkyl carbocation are given above. can be explained in terms of inductive effect and hyperconjugation in terms of the above principle. First, inductive effect. This is the main factor operating in determining the relative stability of carbocation. As a very known, the alkyl group are more electroreleasing than hydrogen. As such, a alkyl group attached to positively charged carbon of the carbocation tend to release electrons towards the carbon due to its plus I effect. In this way, the positive charge on the carbon get towards on the carbon get dispersed. This dispersal of the charge stabilizes the carbocation. Now, the more the number of alkyl groups, greater is the dispersal of positive charge, and therefore more is the stability of carbocation. This is why a tertiary carbocation having 3 alkyl groups attached to the positive carbon is more stable than a secondary carbocation with 2 alkyl groups. The secondary ion in turn is more stable than the primary carbocation having only 1 alkyl group. The methyl carbocation does not have any. The methyl carbocation does not have any alkyl group and is therefore the least stable. Tertiary carbocation, then secondary carbocation, then primary carbocation, then methyl carbocation, which is least dispersal of positive charge, so least stable. It is quite evident that the presence of electron withdrawing substituent, that is minus I, will destabilize the carbocation by intensifying the positive charge on carbon. Second, hyperconjugation. The concept of hyperconjugation is also to some extent responsible for the observed order of relative stability of carbocation. Hyperconjugation can take place here through the overlapping of sigma orbital of sigma CH bond of alkyl group and the empty p orbital of carbocation, taking CH C positive to represent a carbocation in general. Delocalization of electrons through sigma p orbital overlap may be shown as, due to this overlap, the dispersed electrons behind together 3 atoms, 2 carbon and 1 hydrogen to some extent. In terms of resonance, the above situation may be depicted as CH C positive. The bond will move in between C and C to remove the positive charge on C. Therefore, H positive will remain. The net result is that in actual structure, CH bond is slightly less than in a single bond. The carbon-carbon bond have some double bond character, while the positive charge is partially accompanied by hydrogen atom. This partial accommodation of positive charge over hydrogen leads to the dispersal of charge and consequently stabilizes the determination of relative stability of different kind of carbocation. It is evident from the above discussion that the stability of carbocation is primarily related to the dispersal of charge carried by the positively charged carbon. The dispersal of charge may be due to the inductive effect, hyperconjugation effect, or resonance effect as explained above. The relative stability of different kind of carbocation can be measured in terms of heterolytic bond dissociation energy leading to the formation of carbocation. AX will give rise to A positive and X negative. On the basis of these values, the decreasing order of stability of some of the common carbocation is given as tertiary butyl is more stable than benzyl, then isopropyl, allyl, N-propyl, ethyl, vinyl, phenyl, methyl. It is to be pointed out, however, that benzyl, isopropyl, allyl carbocation are more easily stable. Similarly, vinyl, phenyl, and methyl carbocation have nearly the same stability. Rearrangement of carbocation 1-2 shift. An important feature of carbocation is that they can undergo rearrangement reaction to form more stable carbocation. These rearrangement involve the shift of either a hydrogen or aryl groups along with the electron pairs from an adjacent carbon to the positively charged carbon. Such a shift are known as 1-2 shift. This shift of hydrogen is known as 1-2 hydride shift, while that of alkyl group is known as 1-2 alkyl shift. The carbon thus formed contain a new charge center and is more stable than the original carbocation. For example, 1-2 hydride shift. N-propyl carbocation on reacting 1-2 hydride shift will give rise to isopropyl carbocation that is secondary more stable. 1-2 methyl shift second. Neopentyl carbocation primarily on reaction with 1-2 methyl shift will give rise to 2-methyl 2-butyl carbocation tertiary, which is more stable. The rearrangement reaction of carbocation are discussed in detail at later stages in the carb anion. What is a carb anion? A carb anion is an anion in which the negative charge is carried by a carbon. This carbon have three bonds with one or more other atoms and possesses a lone pair of electrons. For example, C triple bond CH is a single carbanion known as acetylene ion. A carb anion may be assumed to be a fragment of a molecule when one of the atom or group similarly bound to a carbon is removed without the bonding pair of electrons. For instance, removal of a hydrogen of methyl pair of acetaldehyde molecule as a hydrogen ion result in the formation of carbon ion as shown below. Acetaldehyde plus OH negative will give rise to carb anion plus H2O. Carb anion constitutes highly stable and one of the more reactive reaction intermediate in organic chemistry. They are more frequently involved in the reaction of aldehyde, ketone, ester, etc. The relativity on is based due to the fact that the negative charge carbon in them have got a lone pair of electron. It has a strong tendency to donate this pair to some electron deficient species. Therefore, carbon ion easily participate in many reactions. Formation of carbocation. There are two main methods by which carbocation are generally as given below. By the dissociation of a molecule in which a atom or group singly attached to carbon leaves it without the electron pair, that is CH. The bond will move on C, give rise to C negative plus H positive. In most of the cases, the leaving group is a proton, hence a base is required to facilitate the process. Thus, the formation of a carb anion is an acid-base reaction. CH bond will move on C plus B negative. This two electrons will move on H, which will give rise to C negative plus pH. Since the presence of electron attacking substituents such as carbonyl, cyano and nitro groups on the carbon carrying the hydrogen makes the hydrogen relatively more stable and therefore more easily removable as a proton. The generation of carbanion from such compounds plays a very important role in organic reactions. For example, OH negative plus CH3CHO will give rise to CH2CHO plus H2O. C2H54 negative plus CH3NO2 will give rise to CH2 negative NO2 plus C2H5OH. To remove a proton from a hydrocarbon, very weak acid, very strong base such as soda amide in liquid ammonia has to be used. For example, CH triple bond CH plus NH2 in the presence of liquid NH3 will give rise to CH triple bond C plus NH3. but aromatic compounds of type triphenyl methyl generate carbanion very easily in the presence of a base. Triphenyl methyl plus OH will give triphenyl methyl anion plus H2O. It may be pointed out that apart from protons, other living groups are also known to lead to the formation of carb anion. For example, RC double bond O will give rise to R negative plus CO2 by the addition of a nucleophile to carbon-carbon multiple atom. C double bond C plus nucleophile, electrons will move from nucleophile to C and one bond will move on another C, give rise to C negative and C nucleophile. But this type of addition occurs only when the double bond is activated through towards nucleophilic attack by electron withdrawing group such as carbonyl, cyano and nitro group. For example, C2H5O negative plus CH2 double bond CH, C triple bond H, C2H5O CH2 CH negative, C triple bond N. Structure of carbanion. The negatively charged carbon of carbanion is in the state of sp3 hybridization, so that the hybridized orbital are directly towards the corner of the tetrahedron. Three of the hydrogen orbitals are involved in the formation of simple bonds with the other atoms, while the fourth orbital contains a lone pair of electrons. Thus, carbocation have distorted tetrahedron and pyramidal structure as shown on the right hand side, but the bond angle around negatively charged carbon are less than 109 degree 28 seconds. This is because lone pair bond pair repulsion is greater than bond pair repulsion is greater than bond pair repulsion. It may be pointed, however, that in case of carbanion in which negatively charged carbon having the lone pair of electrons is in conjugation with a multiple bond, the carbanion have a planar structure. Some common example of carbanion having planar structures are given below: allyl carbanion, benzyl carbanion, acetyl carbanion. Classification of carbanion and their order of stability. Like carbanion, carbocation, carbanions can be classified as primary, secondary and tertiary according to the negative charge is carried by primary, secondary or tertiary. In addition, methyl carbanion is considered to be a special case. Thus, we have methyl carbanion, ethyl carbanion, isopropyl carbanion, tertiary butyl carbanion, which is tertiary. Order of stability of different classes of carbanion has been given as below. First methyl, then primary, then secondary, then tertiary. Free radical. What are free radical? A free radical is an atom or group of atom having an odd or unpaired electron. It is donated by putting a dot against the symbol of atom or group of atom. For example, Cl stand for a chloride free radical, while CH3 dot denotes a methyl free radical. Free radicals are electrically neutral species which are usually formed by the homolytic cleavage of molecule in reaction taking place in gas phase or in a nonpolar solvent. For example, C bond Cl. One electron will move on Cl, giving rise to 2Cl negative radical, 2Cl free radical. Benzyl peroxide, in between the O which are in between, one bond will move on one O and other will move on another, giving rise to 2 benzoyloic free radical. Due to the presence of odd electrons, free radicals are paramagnetic in nature. Free radicals are highly short-lived species. These are extremely reactive, and as soon as they are formed, they intermediately participates in some further reactions. Their greater relativity is due to the tendency of odd electrons in them to get paired up. Formation of free radicals. There are two main methods in which formation of free radicals are usually formed. First, by terminal or photochemical homolysis of a covalent bond. For example, tetramethyl lead on heating give Pb plus methyl free radical. Benzoyl peroxide on heating will give benzoyl free radical, phenyl free radical plus 2CO2. Diacetyl on heating with on treatment with sunlight will give acetyl free radical. By oxidation reduction reaction involving gain or loss of a simple electron, for example Rc double bond O minus 1 electron will give rise to Rc double bond O, or radical will give rise to R radical plus CO2. Structure of free radical. It may be pointed out that in case of free radical containing carbon, the state of hybridization of carbon having odd electrons is not clearly stabilized. However, there is a strong evidence to indicate that most of the alkyl free radicals in such a methyl radicals are actually planar. This means that carbon atom carrying the odd electrons is in sp2 hybridized state. The three coplanar hybrid orbitals are involved in the formation of three single bonds with other atom. The unhybridized p orbitals, which leads in a plane or at a right angle to the plane of hybrid orbital, carried the odd electrons. The bond angle around the carbon carrying the odd electrons is approximately 120 degree each. Classification of free radical and their order of stability. Alkyl free radical are classified as primary, secondary, or tertiary according to the odd electron is carried by the primary, secondary, or tertiary carbon atom. But methyl free radical having only one carbon is treated with a special case. Thus, we have methyl free radical, ethyl free radical, isopropyl free radical is secondary, and tertiary butyl free radical is tertiary. The order of stability of different types of free radicals relative to the alkane from which they are obtained is derived is formed to be tertiary, secondary, primary, then methyl. This order is derived from the bond dissociation energy involved in their formation. The lesser the bond dissociation energy in the formation of carbocation, the more is the stability. To illustrate the above statement, let us consider the homolytic physics of an alkane into a alkyl radical and a hydrogen atom, that is RH will give R radical plus H radical. It is apparent that the delta H of such a dissociation process may be equal to the bond dissociation energy of the bond between the concerned hydrogen and the carbon of the alkyl group. A study of delta H of several reactions involved the dissociation of different alkanes to form different classes of alkyl radical showed that the amount of energy required to form various classes of alkyl radical are in order: methyl, primary, secondary, tertiary. If more energy is required to form one radical than the other, it means that relative to the alkane from which it is formed, the radical contain more energy than the other and is hence less stable. Thus, it may be concluded that relative to the parent alkane in each case is the order of stability of free radical is tertiary, secondary, primary, methyl. Carbenes. What are carbenes? Carbenes are neutral divalent chemical species in which a carbon is covalently bonded to two atoms and has got two non-bonding orbitals having two electrons between them. In other words, carbene contains a neutral atom having 6 electrons in the valence shell, each of which two are unstable. The most common carbenes are CH2 methylene and CCl2 dichloromethylene. Carbenes are having highly reactive species having a very short lived period. Types of carbenes. An interesting feature of carbene structure is that it may exist in two distinct shapes. First, singlet carbene. These are carbenes in which unsaturated electrons are paired, that is, they are present in different orbitals. Triplet carbene. These are carbenes in which unshared pair are not paired, that is, they are present in different orbitals. For example, methylene carbene can have either of the following two structures depending upon its mode of formation: singlet methylene unsaturated electron paired, triplet methylene unshared electron pairs. Triplet carbene represent biradical, that is, divalent free radical. Formation of carbene. There are two methods generally employed for the generation of carbene: by the thermal or photochemical decomposition of aliphatic diazonium compounds, ketones or cyclopropanes or oxyrenes. For example, diazomethyl on treatment with sunlight or heat will give methylene carbene plus N2. Ketene on treatment with sunlight or heat will give CH2 plus a CO. Phenyl cyclopropane or phenyl oxyrene on treatment with sunlight or heat will give CH2 plus C6H5 CH double bond CH2 by the action of a base on suitable halogen compound. This method is usually employed for the generation of halogen carbenes, and the base commonly used is potassium tert butoxide. For example, chloroform plus tertiary butoxide ion will give CCl3 plus CH3 thrice COH, which will further give CCl2 plus Cl negative. It may be noted that in the above reaction, H positive and Cl negative are removed from the same carbon, that is, alpha elimination takes place. A well-known example of a reaction in which carbene is formed as a intermediate is Riemann-Timmon reaction of phenol to give salicylaldehyde. It involves the formation of dichlorocarbene CCl2 as an intermediate. Phenol plus CHCl3 plus 3KOH will give salicylaldehyde plus 3KCl plus 2H2O. Structure of carbene. In singlet carbene, the central carbon is in state of sp2 hybridization of the 3 sp2 hybrid orbital. Two are used in forming two single bonds with the monovalent atom or group attached to carbon. The third sp2 orbital containing the unshared pair of electrons, while the unhybridized p orbital is empty. This structure shows single methylene and triplet methylene. In triplet carbene, the central carbon is in the state of sp hybridization. The two sp hybridized orbitals are used in forming single bond with the two monovalent atoms or group attached to carbon. The two unhybridized p orbital contain one unshared pair electron each. Relative stability of carbene and their explanation. It has been found that triplet carbene are lower in energy and therefore more stable than singlet carbene. This is because placement of two electrons in a single orbital is singlet methylene, involving electron repulsion energy which must be overcome to pair the two electrons in the same orbital. On the other hand, in triplet carbene, the two electrons occupy different orbitals and the electron repulsion is much less. As a result, singlet methylene have higher energy than triplet methylene. The difference in energy is about 37.6 to 46 kilojoule per mole. Comparison of singlet and triplet carbene. Singlet carbene, in this Two unshared pair are present as a pair in one orbital. Triple carbon. In this, the two unshared electron pairs are present as two unpaired electrons in different orbitals, and thus it represents a biradical. These are relatively less stable. Triplet carbons are relatively more stable. In singlet carbon, the central carbon is sp2 hybridized. In triplet, it is sp hybridized. Nature of reagents. When two substances react together, one of the substances is regarded as the attacking reagent, while the other is regarded as substrate, that is the substance which gets attacked. The new substance formed as a result of the reaction are known as product. Thus, the occurrence of a chemical reaction may be depicted as substrate plus attacking reagent will give product. It may be pointed out that the term attacking reagents is usually employed for the substance whose presence brings about a chemical change in the given substance, that is substrate, to form the product. But the use of the two term is purely relative. A particular substance may be termed as the substrate in one reaction and an attacking reagent in the other. However, the following conversions are generally followed in the use of the two terms. First, in a reaction between an organic and inorganic substance, the organic substance is treated as the substrate, while the inorganic substance is taken as the attacking reagent. For example, iodoethane plus Ag plus aqueous KOH will give C2H5OH plus Ki. Second, in a reaction between two organic substances, the substance which supplies the carbon atom in the formation of a new bond between carbon atom and a heteroatom is treated as a substrate. The other substance is taken as the attacking reagent. For example, ethanoic acid, which is substrate, plus ethanol, attacking species, which give new bond formed. In a reaction between two organic substances involving the formation of carbon-carbon bond, one of the substance is arbitrarily assumed to be the substrate, while the other is taken as the attacking reagent. For example, benzene plus ethoxyl chloride will give acetophenone plus HCl. Classification of reagents. There are three types of attacking reagents taking part in organic reaction. These are free radicals. Their formation and reactivity have already been discussed. Second, electrophilic reagents. An electrophilic reagent or an electrophile, that is electron-loving particle, is a reagent containing an atom which is deficient in electron. Because of the presence of electron deficient atoms, such as a reagent try to seek electrons from one other source and thus behaves as a Lewis acid. It attack a molecule at the point of high electron density. Type of electrophiles. There are two types of electrophile. First is positively charged ion or positive electrophile. Positively charged ions such as hydrogen ion, hydronium ion, chlorinium ion, nitronium ion, and carbocation act as electrophilic reagent. Neutral electrophile. These are electrophile reagents in which the electron deficient atom does not carry any charge. For example, AlCl3, FeCl3 and BF3 belong to this category. There are certain substances in which the central atom have a complete octet of electrons, and still it has a tendency to coordinate more electrons due to the presence of empty d orbital. SnFCl4 affords an example of such a electrophile. Carbene act as an electrophile because the atom in them have only 6 electrons rather than an octet. Reaction involving Electrophilic reagents are known as electrophilic reactions. Third, nucleophilic reagents. A nucleophilic reagent or a nucleophile, that is nucleus loving particle, is a reagent containing an atom having an unstable shared or electron pair of valence electron. Because of this free pair of electrons, such a reagent is in in search of a site with which to share electrons, and in this way behaves as a base. Lewis concept of bases: it attacking a molecule at a point of low electron density. For example, consider a OH negative ion, the or oxygen present in the ion containing unshared pair of electrons. Due to this reason, OH negative ion attack any molecule containing a center of low electron density so as to share the electrons at that point. Types of nucleophile. Nucleophiles are also of two types. First, negative nucleophile or negatively charged ion. All negatively charged ions such as hydroxyl ion, halide ion, alkoxide ion, cyanide ion, and carbanion, such as act as nucleophilic reagent. Neutral nucleophiles: these are neutral reagents which contain atoms with lone pair of electrons but does not carry any charge. Water, ammonia, and alcohol are neutral reagents. Reaction involving nucleophilic reagents are known as nucleophile reaction. To be precise, all electrophiles and nucleophiles should be capable of forming covalent bonds when they participate in the reaction. For this reason, positive ions such as sodium ion having noble gas configuration are not treated as electrophiles because they cannot form covalent bond as they already have noble gas configuration. Classification of organic reaction. The organic reaction may be broadly classified in the following categories. These are substitution or displacement reaction, addition reaction, elimination reaction, rearrangement reaction, isomerization reaction, condensation reaction, molecular reaction. Substitution reaction. A substitution reaction is that which involves the direct replacement of hydrogen atom or some other group of molecules by some other atoms or group without any change in the structure of a remaining part of the molecule. The product obtained is known as a substitution product, and the new atom or group which enters the molecule is known as a substituent. For example, when chlorine reacts with methane in the presence of diffused sunlight, the hydrogen atom are replaced by chlorine atoms one after the other, leading to the formation of substitution products. CH4 plus Cl2 will give methyl chloride plus HCl. Similarly, the reaction of methyl iodide with an aqueous solution of potassium hydroxide to form methyl alcohol is a substitution reaction. Methyl iodide plus aqueous KOH will give methyl alcohol plus Ki. Substitution reaction may involve free radical, electrophilic, or nucleophilic reaction. Accordingly, there are subdivided as: first, free radical substitution reaction. For example, hydrogenation of alkanes is a free radical substitution reaction. For example, Cl2 in the presence of sunlight will give 2Cl radical. CH4 plus Cl radical will give CH3 radical plus HCl. CH3 radical plus Cl2 will give CH3Cl plus Cl2 radical, and so on. Electrophilic substitution reaction. Nitration and sulfonation of benzene are important examples of electrophilic substitution reaction. Benzene plus nitronium ion will give nitrobenzene plus H positive removed by the base. Nucleophilic substitution reaction. Substitution reaction of alkyl halide are nucleophilic substitution reaction. HO negative plus CH3I will give CH3OH plus I negative methanol. Addition reaction. An addition reaction involves the combination between the molecules of two reacting substances to form a single compound known as addition products. On the reactants in such reaction always contains double or triple bond in its molecule. For example, ethylene plus Br2 will give ethylene dibromide. Addition reaction may also involve free radical, electrophilic or nucleophilic reagents. As such, they are subdivided as free radical addition reaction. Addition of HBr to alkane in the presence of benzoyl peroxide is a well-known example of free radical addition. CH3 CH double bond CH2 plus HBr in the presence of benzoyl peroxide will give N-propyl bromide. Electrophilic addition reaction. Most of the addition reaction of the alkane are electrophilic addition reaction. CH3 CH double bond CH2 plus HX will give CH3 CH positive plus C into CH3 plus X negative. CH3 CH positive CH3 plus X negative will give CH3 CHX CH3. Nucleophilic addition reaction. Aldehyde and ketone undergo nucleophilic addition reaction. Acetaldehyde on reaction with Cn negative will give CH3 CHO negative Cn. On reaction with H positive will give acetaldehyde cyanohydrine. Elimination reaction. These reactions involve the loss of atoms or group of atoms from a molecule to form compound containing double or triple bond. Thus, these reactions are essentially the reverse of addition reaction. The common reaction of this type involve the elimination of atoms or group from adjacent carbon atom to yield alkene. For example, propyl chloride plus alcoholic KOH will give propylene plus H2O. Elimination reaction are further divided into two types as given below. Unimolecular elimination reaction. These are the elimination reaction in which rate determining step involved only one molecule. For example, dehydrohalogenation of a tertiary alkyl halide usually produced by E1 mechanism. Tertiary butyl chloride plus alcoholic KOH will give CH3 CH3 double bond CH2 plus KCl plus H2O. Bimolecular elimination reaction. These are the elimination reaction in which rate determining step involve two molecules. For example, primary alkyl halide such as N-propyl chloride shown above generally undergoes dehydrohalogenation by E2 mechanism depending upon the relative position of atoms or group eliminated. These reactions are also classified as alpha, beta or gamma elimination reaction. Alpha elimination reaction. These are the reaction in which loss of two atoms or group occurs from the same atom of the substance. For example, chloroform plus OH negative will give dichlorocarbene plus H2O plus Cl negative. Beta elimination reaction. In this reaction, loss of two atoms or group occurs from adjacent atom of the substance. For example, ethanol in the presence of concentrated H2SO4 and heat will give ethane plus H2O. Alpha elimination reaction. In this reaction, loss of two atoms or group occur from alpha or gamma position of a molecule, giving rise to the formation of three-membered ring. 1,3-dibromopropane in the presence of Zn dust and heat will give cyclopropane plus ZnBr2, which is fluent reaction. Rearrangement reaction. These reactions involve either the migration of functional group from one atom to the other or the complete rearrangement of the chain of carbon atom present in the compound to form a new product. For example, 1-bromobutane in the presence of 573 Kelvin temperature and AlCl3 will give 2-bromobutane. N-butane in the presence of AlCl3 or HCl heat in a sealed tube will give 2-methyl propane. This rearrangement also takes place through the formation of electrophile, nucleophile or free radical intermediates. It is interesting to note that the preparation of first organic compound, that is urea, to be synthesized in the laboratory involve a rearrangement reaction. Ammonium cyanate in the presence of heat will give urea. Isomerization reaction. These reactions involve the conversion of one isomer into another so that the molecular formula and carbon skeleton of the reactants and products always remain the same. For example, conversion of trans-2-butene to cis-2-butane and vice versa is a geometrical isomerization reaction. Tertiary 2-butene in the presence of sunlight will give cis-2-butene. Condensation reaction. These are the reaction in which two or more molecules of the same or different reactants combine to form products with or without the elimination of a simple molecule such as water or alcohol. For example, when acetaldehyde is treated with a dilute alkene, two molecules of acetaldehyde combined to form 3-hydroxyl butanol. The reaction is known as aldol condensation. Acetaldehyde 2 moles in the presence of dilute NaOH will give 3-hydroxyl butanol or aldol. Molecular reaction. These are the reactions which involve the reorganization of covalent bonds either intramolecularly or intermolecularly through cyclic transition state under the influence of heat or light. These reactions do not require any catalyst and no ionic or free radical intermediate is involved. These are collectively called pericyclic reaction. Electrocyclic and cycloaddition reaction are typical examples of such reaction. First, electrocyclic reaction. These reactions involve conversion of an acyclic diene to a cyclic alkene and vice versa. For example, buta-1,3-diene in the presence of sunlight or heat will give cyclic transition state which will further give cyclobutene. Cycloaddition reaction. These reactions involve addition of two unsaturated molecules of the same or different substances to form cyclic products, and an example of this type is 4 plus 2 cycloaddition reaction given below. The student will come across the detailed mechanism of various reactions at appropriate places in the text. Energy changes during reaction. All chemical reactions involve the breaking and making of bond. Since energy is required to break a bond while energy is released in the formation of a bond, the occurrence of chemical reaction is always accompanied by energy change in one form to the another. We will therefore now present briefly certain basic concepts regarding energy change such as enthalpy of reaction, energy of activation and transition state. Heat or enthalpy of reaction. Heat or enthalpy of a reaction is the total energy change which accompanies the conversion of the definite number of moles as required by the balanced equation of a reaction into the product. It is possible to calculate the enthalpy of reaction on the basis of bond dissociation energy of various bond broken and formed during the reaction. For instance, let us consider the following hypothetical reaction. Let us suppose that x1, x2, x3 and x4 represent the bond dissociation energy of the respective bond involved in the reaction. During the reaction, two bonds A, B and C, D are broken while new bonds AC and BC are formed. The two bonds broken require a total energy of x1 plus x2 kJ per mole of energy, while the two bonds formed liberate an energy of x3 plus x4 kJ per mole of energy. Therefore, the total energy change during a reaction, or in the other words, heat of a reaction, should be x1 plus x2 minus x3 plus x4. It is apparent that if the energy consumed, that is x1 plus x2, is more than the energy released x3 plus x4, there will be overall consumption of the energy, that is the reaction would be endothermic and delta H would have a positive value. On the other hand, if energy consumed x1 plus x2 is less than the energy released x3 plus x4, there would be net liberation of energy, that is the reaction would be exothermic, and delta H would have a negative value. Thus the reaction between methane and chlorine is methane plus Cl2 will give CH3Cl plus HCl. Delta H will equal to 433 plus 242.5 minus 350 plus 430 will give minus 104.5 kilojoule. Is the exothermic reaction since it results in the liberation of 104.5 kilojoule of energy for each mole of methane converted into methyl chloride. On the other hand, the reaction between methane and iodine is an exothermic reaction. CH3H plus I2 will give CH3I plus HI. Delta H is equal to 433 plus 151 minus 234 plus 297 will give 53 kilojoule. Energy of activation and theory. Collision theory. An important feature of most of the reaction, whether exothermic or endothermic, is that the reaction require some extra energy for the reaction to take place. To understand the reason for this, let us recall that according to collision theory of reaction, the primary condition for a reaction to take place is that the reacting particle must come in contact or collide with each other. But all such collision do not result in the formation of product. In order to be effective in bringing about the reaction, a collision should fulfill two conditions. First, the colliding particle must have a certain minimum amount of energy known as threshold energy. The collision particle must have properly oriented with respect to each other at time of collision. As far as the energy factor is concerned, most of the reactant molecules do not possess sufficient energy in their ground state for effective collision to take place. A result, when each molecules collide with each other, no bond breaking or making takes place. The collision particle bounce back as such. Therefore, extra energy is needed by the reactant to form the product. The minimum amount of additional energy required by the reactant to undergo effective collision is known as activation energy EA. It is numerically equal to the difference between threshold energy and ground state energy of the reaction. Most of the organic reactions have activation energy in the range 40 to 150 kilojoule per mole. If the activation energy has lower value, the reaction can take place either at room temperature, or on the other hand, reaction with high activation energy takes place only on heating. Energy barrier to the reaction. The concept of activation energy means that the reactant have to be activated or raised to a higher energy level before they form the product. On the other hand, in other words, there exists a certain energy barrier between the reactant and the product. In depicting the progress of a reaction, this barrier is generally represented as the energy hump, which has to be summoned before the reaction can be completed. It may be completed to pass on the top of a hill separating two valley on the two sides of the hill. To remove from one valley to the other, one must move up the hill and cross the pass. Similarly, the reactants must move up the energy level and cross the energy barrier or hump to yield the product. It is interesting to note that even though a chemical reaction involving breaking and making of the bond, the total processes are not perfectly synchronized. At the same time, the energy released through bond formation is not completely available for bond fission. This also explains why the reaction required extra energy for the reaction to take place. Transition state theory. Energy diagram of a reaction. The transition state theory have been very useful in understanding the mechanism of organic reaction and the energy changes take place during the reaction. According to this theory, The reaction does not change directly into the product, but what happens is that when the reaction molecule come in contact with each other, it leads to the formation of a highly unstable arrangement of atoms whose energy corresponding to the energy barrier separately the reactant and the product. The higher energy species that thus formed is known as activation state or transition state. For example, in the single step reaction represented by the equation a plus b minus c will give a plus bc will give ab plus c. For the higher energy transition state may be represented as these dotted line indicate partial bond a dot b dotted line C. The transition state merely represent a probable arrangement of atom corresponding to the energy barrier in which a bond is partially but not completely broken and a new bond have begun to form but is not yet completely formed. It does not represent a substance which can be isolated or even detected. As soon as this transition state is formed, it split into the product. Thus, the complete reaction sequence may be represented as reactant, then transition state, then further gives product. The reactant is A plus BC will give this transition state A dot line B dotted line C, which will further give AB plus C as product. Energy diagram for multi-step reactions. A reaction can proceed from reactant to product either directly in a single step known as concerned reaction, or it and takes place through two or more steps which include the formation of one or more intermediates. Since the reactant is directly converted into the product without the formation of any intermediate substance in a concerned reaction, the energy diagram of such reaction have only the energy minima corresponding to the reactant and the product and energy maximum corresponding to the transition state as shown in figure 3.2. Most of the reaction of organic compounds are multi-step reaction involving the formation of one or more reactive intermediates. Therefore, let us now consider the complete energy diagram of multi-step reaction with the help of two-step reaction involving one reactive intermediate. Such a reaction involves the formation of two transition states as shown below. Reactant transition state 1, reactive intermediate, this is step 1. In step 2, reactive intermediate will give transition state 2, which will further give product. In such reaction, we draw an energy diagram for each of the individual step and then join them in middle as the product of step 1, that is reactive intermediate, as the starting material for step 2. Since the intermediate has higher energy than either the reactant or the product, it is very relative and may or may not be isolated. However, unlike the transition state, the intermediate have a measurable lifetime. Development and structure of transition state. Hammond's postulate. In order to fully understand reaction, it is necessary to completely understand the structure and energy of the transition state which lead to the formation of product. But the transition state have only a transitory existence. As soon as it is formed during the course of reaction, it changes into a more stable species. But it is possible to have an idea of the structure of a particular transition state from the reaction energy diagram with the help of Hammond's postulate. Hammond's 1955 advanced generalization known as Hamilton postulate to correlate the energy and structure of transition state. According to this postulate, structure of the transition state most closely resemble the structure of the stable species that lies closer to it in the energy. For example, in a strongly endothermic reaction, the energy level of the transition state is much closer to that of the product than reactant. Thus, the transition state would be expected to closely resemble to the product in structure as well. On the other hand, in the strongly exothermic reaction, the transition state is energetically much closer to the reactant than the product. As a result, it have a strong resemblance to the reactant structurally. For a two-step reaction, the first transition state may structurally resemble either the original reactant or the intermediate, whichever is closer to it in energy. The second transition state is then may resemble structurally either the intermediate or the final product accordingly as which is energetically close to it. Effect of catalyst on the transition state. Many reactions which we study involves the use of some suitable catalyst to increase the rate of reaction. What the catalyst does is such reaction is to provide an alternate path for reactant to product with a lower energy transition state. Thus, the catalyst lower the energy of activation required for the reaction so that the rate of reaction increases. It must be pointed out, however, that the delta H or delta G for a reaction remains unchanged even in the presence of catalyst, assigning formal charges on intermediate and other ionic species. While studying the various reaction intermediate, it has been found that these species have either carry positive or negative charge, or they must be neutral in character. In order to predict whether a given species carries some charge or not, we now present a very simple known as formal charge method for charge explanation or intermediate. Formal charge, it is the amount of positive or negative charge which can be assigned to certain atoms of a species in order to know whether the species act as a whole carries some charge or not. The calculation of formal charges involves the comparison of a number of valence electrons in a neutral atom in the free state and the number of valence electrons associated with the atom in the bounded state. The difference between the two values gives the formal charge on the atom in the given species. That is, formal charge on an atom in a given species is equal to number of valence shell electron in the free atom minus number of valence shell electron in the bounded atom. Calculation of number of valence electron in the bounded state. To calculate the number of valence electron associated with an atom in a bounded state, first, number of electrons shared between two atoms are directly divided equally between the two atoms that shared them. This means that even though the electrons are shared between the two atoms, it is still true as if each atom owns one electron of the shared pair. The number of non-bounded valence electrons of an atom are assigned exclusively to that atom. The sum of the number of electrons assigned as above gives the number of valence electron in the bounded atom. This is also sometimes referred to as the average electron. That is, number of electrons in the bounded atom or average electrons is equal to 1 by 2 of number of shared electrons plus number of non-bounding electrons. Therefore, the formal charge on a bounded atom may also be expressed as formal charge on an atom is equal to number of valence electrons in the free atom minus 1 by 2 into number of shared electrons plus number of non-bounded electrons. Formal charge on a species as a whole. Knowing the formal charge on each atom in a given species, the formal charge on the species as a whole can be found by adding together the formal charges on various atoms. That is, formal charge on a species is equal to sum total of formal charges on all the atoms in the given species. We now illustrate the complete procedure by considering the example of the simple molecule methane. CH4. It is apparent from this structure that carbon is surrounded by 8 electrons which are shared with 4 hydrogen atoms. Therefore, the number of valence electrons associated with carbon in methane is 1 by 2 into 8 is equal to 4. Since the number of electrons in a free carbon atom is also 4, The methane carbon is electrically neutral. In other words, there is no formal charge on carbon atom in methane. We can also arrive at the same conclusion directly. Formal charges on carbon. Number of valence shell electron in free carbon minus 1 by 2 into number of shared electron plus number of non-bounding electrons is equal to 4 minus bracket 1 by 2 into 8 plus 0 bracket close will give 4 minus 4 is equal to 0. Each hydrogen atom in methane is surrounded by 2 electrons which are shared with carbon. Therefore, formal charge on each hydrogen is equal to 1 minus bracket 1 by 2 into 2 plus 0 bracket close will equal to 0. Therefore, formal charge on methane molecule is equal to formal charge on carbon plus 4 into formal charge on each hydrogen, which will give 0 plus 4 into 0, which is equal to 0. It is of course well known that methane molecule have no electrical charge. Let us now compute the formal charges on some of the intermediates already studied. First, free radical. It has been stated earlier that free radicals are electrically neutral species. To justify this, let us consider the methyl radical, which is the simplest radical. The carbon is surrounded by 6 bounded electrons shared with 3 hydrogen and 1 non-bounding electron. Each hydrogen is surrounded by only 2 shared electrons. Therefore, formal charge on carbon is equal to 4 minus bracket 1 by 2 into 6 plus 1 a bracket close minus is equal to 0. Formal charge on each hydrogen is equal to 1 minus bracket 1 by 2 into 2 plus 0 bracket close, which is equal to 0. Formal charge on methyl radical is equal to formal charge on carbon plus formal charge on hydrogen, which will give 0 plus 3 into 0 is equal to 0. Second, carbocations. The positive charge on the carbocation may be varied by considering the case of methyl carbocation. It may be easily seen that formal charge on the carbon is equal to 4 minus bracket 1 by 2 into 6 plus 0, which will give plus 1. Formal charge on each hydrogen will equal to 2 minus bracket 1 by 2 into 2 bracket close, which will give 0. Therefore, formal charge on carbocation will be equal to plus 1 plus bracket 3 into 0 bracket close, which will give plus 1. Third, carbanion. It is well known that carbanion are negatively charged species in which a carbon atom carries negative charge. To rationalize this, we may consider the structure of methyl carbanion. Formal charge on carbon is equal to 4 minus 1 by 2 into 6 plus 2 is equal to minus 1. Formal charge on each hydrogen, which is equal to 1 minus 1 by 2 into 2 plus 0, which will give 0. Therefore, formal charge on carbanion is equal to minus 1 plus 3 into 0, which will give minus 1. Carbene. The simplest carbene is methylene. Formal charge on carbon is equal to 4 minus 1 by 2 into 4 plus 2, which will give. Formal charge on each hydrogen will equal to 1 minus 1 by 2 into 2, which will equal to 0. Formal charge on carbene is equal to 0 plus 2 into 0 will give 0. Carbenes are neutral species. Nitrines. The neutral character of nitrines may be verified with the formal charge calculation on methyl nitrene. Formal charge on carbon is equal to 4 minus 1 by 2 into 8 plus 0, which will give 0. Formal charge on nitrogen is equal to 5 minus bracket 1 by 2 into 2 plus 4 bracket close, which will give 0. Formal charge on each hydrogen is equal to 1 minus 1 by 2 into 2, which will give 0. Therefore, formal charge on nitrene is equal to formal charge on carbon plus formal charge on nitrogen plus 3 into formal charge on hydrogen, which will give 0 plus 0 plus 3 into 0. It is equal to 0. Therefore, our chapter is completed. Thank you.